أهلا بيك يا سارة. I allowed you recording. Okay, now inshallah today we are going to start a new chapter, which is the transition metals and their chemistry. Now, if we look طبعا in the periodic table, we will see that the elements that are present. أهلا بيك عبد العزيز. I allowed you recording if you'd like to. You will find that in the periodic table, we will see that the elements that are present on the left-hand side, of course, as we know them, the alkali metals, then the alkaline earth metals, we call them S block elements. These are called the S block elements because, as you know, of course, that when you fill the electronic configuration, you will find that all of them will end up with the S subshell. That's why we call them the S block elements. If we look on the other side, from group 3 to group 0 or group 8, we call these P block elements. And we used to call these the transition metals. We used to call them transition metals. But of course, this name is not very correct. We have to say, instead of calling them transition metals, we are going to call them as the others. We are going to call them D block elements, because not all of them are transition metals. We will see that some of them are not transition metals, but most of them are transition metals, but some are not. So we come to the definition of what is a transition metal. We say that a transition metal is a D block metal or element, is a D block element that has at least one stable ion, or we can say only one ion, at least one ion with incompletely filled D subshell. So transition metals are metals that have at least one ion or more, of course, but at least one ion with incompletely filled D subshell. And of course, we are going to see why some of these transition metals, a few of them, are not transition metals. They are called D block elements, but we cannot call them transition metals, because from the definition, it says that a D block element that has at least one stable ion with incompletely filled D subshell. And of course, when we talk about the electronic configuration, we will see which one of them or which of these is not a transition element. Then that's why we call them D block elements, but we cannot say in general that they are called transition metals. No, we call them D block elements. Okay. Now, if we come to the characteristics of transition metals as we know them from O level, we say that transition metals are hard solids. They have high melting and boiling points. They can act as catalysts. We know that, of course, most of them act as catalysts, or their compounds also can act as catalysts. They form colored ions and compounds. We are going to discuss this part in details. They form ions with different oxidation numbers, and they form ions with incompletely filled D orbitals. That's what I was talking about. It's a main point in the definition of a transition metal, that it should form at least one ion with incompletely filled D subshell or D orbitals. Okay, so we come to the electronic configuration of these elements and see why some of them are not transition metals. Now, when we talk about the electronic configuration of transition metals, they start with scandium, scandium-21. We say that its electronic configuration is 1s2 2s2, 2p6, 3s2, 3p6, because we are going to study only the first row of the D block elements, 1s2, 2s2, 2p6, 3s2, 3p6, and then what comes after 3p6? Who remember? Yes, yes, Sarah, what comes after 3p6? Yes, yeah, Karam, تفضل. Yes.
4s.
Yes, excellent. It's the 4s. No, Yasin. الأول ال 4s and then the 3d, isn't it? يعني هنا we write 3d, but we fill the 4s first by the 2 electrons. We fill always the 4s first. Yes, ya Jumana. And then we have 3d1. So as Karam said, we are going to fill the 4s first and then the 3d. We write the 3d before the 4s, but we fill the 4s before the 3d. If you write the opposite, if you put the 3d after the 4s, it's okay. It's not wrong, but it's better to write the 3d first and then the 4s. Okay, but when you fill the 4s by the 2 electrons and then the 3d by this electron, which is the 21st. So this is the first element, which is scandium. Now, if we look at the second element, which is titanium, 22, we find, the second element is, yes, titanium. We find that it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, we leave it empty. And then we fill 4s by 2 electrons, and then the other 2 electrons are filled here in the 3d. For vanadium, okay, Abdullah, can you tell me the electronic configuration of vanadium? 23.
1s2, 2s2,
Yes.
2p6,
Yes.
3s2, 3p6, 3d3, 4s2.
Yes, excellent. We fill 4s first and then the 3d by 3 electrons. Excellent. Now, when we come to chromium, we say that chromium is an exception case. If you remember, chromium is an exception case. The electronic configuration that we should write is 1s2, 2s2, 2p6, 3s2, 3p6, 3d, we leave it empty, 4s2, and then we fill this by 4 electrons, the 3d subshell by 4 electrons. But if you write this, we said that this is wrong. This is completely wrong, because we have a rule that says that if a subshell is half filled or completely filled, this makes it greater, or this will give it a greater stability. Yes, excellent, Yejumana. So the rule says that if you have a subshell that is half filled or completely filled, this will give it greater stability. So if we look at chromium, it's 3d subshell that consists of 5 d orbitals, and here the 4s. You will find that the 4s is filled by 2 electrons, and the 3d has only 4 electrons, which means that if this last electron was filled, this will give the chromium a greater stability. That's what the rule says. It says that if you have a subshell that is half filled, so here for the D subshell, half filled means it is filled with 5 electrons, or completely filled, this means that it could be filled by 10 electrons. But for chromium, if it is half filled, it means that if another electron was filled here, this will give chromium greater stability. That's why chromium will take an electron from the 4s, and the electronic configuration will be 3d5 4s1, because we assume that 4s and 3d are overlapping together. The 4s is not away from the 3d by a big amount of energy. I mean, they are overlapping together, which means that they are considered as if they are only one shell together. Because they are overlapping together, they are considered as if they are together. That's why if an electron is transferred from the 4s to the 3d, this is okay. And if we fill the chromium in this way, then the 3d subshell will be half filled, and in that case also the 4s is half filled, and this gives it greater stability. So if you write the electronic configuration in this way, it's wrong. For chromium, it should be filled by 3d 5 electrons, and then 4s, of course, 4s by 1 electron, and then the 3D by 5 electrons. What do you mean by the arrows, يا ياسين? What do you mean by
هو
that?
ده أنا مش فاكره أوي بصراحة.
اللي هو ايه؟ يعني
لا هو البوكسز
الالكترونيك
جواها
كونفيجريشن
أيوه
قصدك تقول؟
دي
الالكترونيك كونفيجريشن في ال 3 دي.
بتاعت الأعرس دي ما مش
ما
فاكر
هي
اسمها إيه.
الاروز معناها الكترون، يعني each arrow represents an electron. ولا انت قصدك ايه؟ مش عارف
أيوه
يعني
دي
مش انت بتقول على ده؟
أيوه بالظبط.
اوكي each arrow represents an electron.
اوكي
واخد بالك يا ياسين؟ يعني هنا you have to fill ال 3D by 4 electrons. يبقى انت بتحط الكترون هنا والكترون هنا والكترون هنا والكترون هنا، مش كده؟ ولا انت قصدك ايه؟ مش عارف.
اوكي تمام يا دكتور.
Okay, Gihad, we say that if you write the electronic configuration as usual, we usually fill the 4s by electrons first, and then we fill the 3D. So if for chromium you have 24 electrons, you are going to fill 1s2, 2s2, 2p6, 3s2. كنا بناخد الكلام ده في الاس. 4s, 4p6, 3p6. And then we fill the 4s before the 3D. So we fill the 4s by 2 electrons and the 3D by 4 electrons. If you count these numbers, you will find them to be 24. Okay? If you count the upper numbers, these are the number of electrons that are filled in each subshell. If you count them, you will find that they are 24. But there is a rule. There is a rule that we took also in AS that says that if a subshell is half filled or completely filled, this gives it greater stability, So if you look at chromium, you will find that the 3D subshell is filled by 4 electrons, which means that if it has an electron here also, it will be half filled, because we know that the D subshell can be filled by 10 electrons. So if it is filled by only 4 electrons, means that there is only 1 electron left for it in order to form 5 electrons in the 3D and will be half filled. If it is filled by 5 electrons, it will be half filled, isn't it? Okay, go ahead. So what will it do? Yes, one of the electrons from the 4s is going to move to the 3D. And so by this way, the 3D subshell will be half filled. 1, 2, 3, 4, 5. These are the electrons that fill the 3D subshell. And the 4s will be filled by 1 electron. And it's okay for both, because both of them now are half filled, and this is satisfied. This gives chromium greater stability. Okay, understand? Okay, thank you so much. Do you have any question here? So these arrows represents the filling of electrons in shells and subshells. Now, after chromium, we come to manganese. Okay, Jomana, thank you so much. We go to the, after chromium, we have manganese. Manganese is 25. So we fill 1s2, 2s2, 2p6, and so on, till we have 4s2, and then till 4s2, this means that we fill 20 electrons. Then there will be 5 left. We are going to place them in the 3D subshell. When we come to iron 26, this means that they are going to fill up till 3D. Of course, we fill this 4s first, and then the 3d6, and so on, until we come to copper, which is the second exception. Copper 29 is the second exception. We fill it 1s2, 2s2, 2p6, 3s2, 3p6. We leave 3d empty. We fill 4s first by 2 electrons, and then there will be left 9 electrons. They are placed in the 3D. But if you write the electronic configuration of copper in this way, this is wrong, because as the rule says, it says that if a subshell is half filled or completely filled, this will give it greater stability, which means that if an electron is transferred from the 4s to the 3d so that the 3d become 3d10 and the 4s will be 4s1, this is the electronic configuration of copper. Whenever they ask you to write the electronic configuration of copper, you have to write it in this way. If you write it in that way, it will be wrong. Okay. Magnesium. What do you mean by magnesium? Not magnesium. You don't write magnesium. Okay, again, I'm going to tell you what are you going to write. Now, sometimes we don't have to write all these shells. We don't have to say 1s2, 2s2, but we go to an upper, if you look here in the periodic table, you will see that if you want to write the electronic configuration in a different way, Yagihad, then this is the row at which the transition elements are present. You go in an upper row. Here we have argon, the inert gas. Argon contains 18 electrons, not magnesium, it's argon. So for scandium, instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, and so on, you can write between brackets argon. Argon means that we have 18 electrons. Yes, Yagihad. So you go upward by only one row and you look at the inert gas that is present, which is argon. So you write between brackets argon. This means that you have written the electronic configuration that we said before, 1s2, 2s2, 2p6. You can put all these in the form of argon between brackets, which means that you filled already 18 electrons. And then you write 3d, 4s2, 3d1. So you can do that with all the others. Titanium, 22, you write argon between brackets, and then you write 3d, you fill the 4s by 2 electrons, and then the 3d. Okay, you can write the electronic configuration this way, and this is correct. Or you can write it in the way that we did before, 1s2, 2s2, and so on. Hello, Yabasma. Okay, understand how to write electronic configuration, or do you have any question? These are for elements, of course. Now, what about the ions? What about the ions? What if I want to write the electronic configuration of the ion? So, for example, if you have iron, iron is 26. So we said 1s2, 2s2, 2p6, 3s2, 3p6, 3d, and we left it empty. 4s2, this makes 20 electrons. There are 6 left, so we put the 6 here. So iron and all transition metals, as we are going to see, they can form more than one ion. So here iron can form either iron +2, or they can form iron +3. If you want to write the electronic configuration of iron +2, so since you added the electrons in the 4s first and then the 3d, the same will be done when you remove the electrons to form the ions, because when we form iron +2, this means that iron lost 2 electrons. From where the 2 electrons are going to be lost? Are they going to be lost from the 3d or the 4s? Do you remember? 4S. Yes, Yanina? I didn't hear you.
From 4s.
Yes, excellent. As we added first the 4s, yes, Yajumana, excellent. As we added first our electrons in the 4s and then the 3d, the same will be done when we remove the electrons. We are going to remove the electrons also from the 4s, which means that the electronic configuration of iron +2 will be 3d6, and we are not going to write the 4s. Or if you would like to write it, you have to write here 0, or you don't write it. And if I want to write the electronic configuration of iron +3, this means I'm going to write 1s2, 2s2, and so on. And then I remove 2 electrons from the 4s and another electron from the 3d, and we are left with 3d5. But sometimes students do what? Sometimes students say, okay, I want to write the electronic configuration of iron +2. I'm going to remove 2 electrons. Okay, so 26 minus 2, this makes 24. So I have to distribute the 24 electrons on the shells. So they write iron +2 electronic configuration, for example, argon, and then they say 4s2 3d, because they fill the electrons 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4. So this is wrong. We don't do that. We don't subtract the number of electrons that we want to remove from the original and then distribute the electrons as usual. We don't do so. We write the electronic configuration of iron as it is, or any element as it is, and then to remove the electrons, as we add the electrons first to the 4s, we have to remove the electrons also first from the 4s. No, Abdurrahman. Abdurrahman is asking, is the 3D having higher energy level than the 4s? No, it's not higher, but they are overlapping. Of course, this is a big, this is a big subject. موضوع ال 3D وال 4s, they are overlapping together. And why the electrons fill the 4s first and then the 3D, this is a big subject. We usually teach it in the third grade in the university. We don't even give it in the first grade, we give it in the third grade. This is something that we okay. So because the 3D and 4s, they are overlapping together. So when we fill the 4s first and then the 3D, and also when we remove the electrons, we remove it from the 4s and then the 3D. Okay, understand all? Or do you have any question? Do you have any question? Okay, thank you, Juman. Now, why we said that? Okay, Yassine, thank you so much. Now, why did we say that some of the D block elements are not transition metals? As you remember, we said that the definition of the transition metal is that a transition metal is a D block element that has at least one stable ion with incompletely filled D subshell. Now, let us look about scandium, which is the first member in the D block elements. We said that the electronic configuration of scandium, let us write it in this way, argon, and then 4s2, 3d1. Now, scandium cannot form except scandium +3. The scandium, the only ion that is formed by scandium is the scandium +3. It cannot form scandium +1, cannot form scandium +2. The only ion that is formed is scandium +3, which means that 3 electrons are removed from the scandium when it changes from scandium to scandium ion. So these 3 electrons are removed from the 4s and the 3d, which means that the electronic configuration of scandium is only argon. Or if we write it 1s2, 2s2, 2p6, 3s2, 3p6, that's all. So we do not consider it a transition metal because we said that the definition states that for any transition metal, it should have at least one ion with incompletely filled D subshell. Its ion doesn't contain any D subshell. It doesn't have any electrons filled in the D subshell. That's why scandium is not considered a transition element. It is a D block element, but not a transition metal because its ion does not contain any electrons in the 3D. Understand me, or shall I repeat? So scandium is not a transition metal. What else? Also, we have zinc, the last element in the first row of the transition elements, or the first row in the D block elements is zinc, and zinc is 30. 30 means that we have argon, and we have 3d10, 4s2. Up till 4s, it means that we have 20 electrons. The 3d has the last 10 electrons to complete 30. Now, zinc has also one ion, which is the zinc +2 ion, which means that these 2 electrons are removed from the 4s. So we have argon 3d10. So if you look at the D subshell, you will find that it is completely filled by electrons. We have 10 electrons filling the 3D subshell, which means that it has no ion with incompletely filled. It must form an ion with an incompletely filled d subshell. Now, if you look at the 3D, it is completely filled. This is the only ion that zinc can form, and its d subshell is completely filled by electrons. So also we cannot consider zinc to be a transition metal. So scandium and zinc are not transition metals. But the rest of the elements in the first row of the D block elements, they are considered, of course, transition elements, because as we've seen, if you look here for iron, when it forms iron plus 2 or even iron plus 3, it has an incompletely filled D subshell. All of the rest, if you form any ion, you will see that its ions will have an incompletely filled D subshell. Okay, understand, or do you have any question? Do you have any question? Type. Okay, now let's see about the, we said that we used to know that transition metals have variable oxidation states, of course, because they have, we can remove more than one electron, as you see here from the electronic configuration. Of course, I think there is here, a mistake here. This is 3d5 for S1, not for S2. This is for S1. No, not for the metal, ya Jumana, for the ion. It should have at least one ion, not metal. It should have at least one ion with incompletely filled D subshell. Okay, understand what I mean? It should have at least one ion, not itself to be to contain an incompletely filled D subshell. No, it should have at least one ion with incompletely filled D subshell. So when you form the electronic configuration of the ion should have an incompletely filled D subshell to be considered a transition metal. But since scandium and zinc, although their metals have electrons in the D subshell, yet their ions either have either for scandium, it does not have any electron in the 3D, or in case of zinc, its ion, the electrons are completely filled. So these two are not transition metals. They are D block elements, but not transition metals. أهلا بك يا محمد. I allowed you recording. Okay, understand ولا في حاجة do you want me to repeat? طيب, as we see here, as the electronic configuration consists of 2 electrons in the 4s or whatever. Here, of course, it should be only 1 electron. Here, this is a mistake in the book. So either you have 4s2, 3d, whatever the number, or you have 4s1 and the number. Then we see that transition metals can form more than one ion. That's why when we were studying in the O level, they usually says that transition metals have more than one ion, or they have variable oxidation numbers, or they have variable oxidation states. It means that every element of these elements in the transition metals can form more than one ion. So you see here, for example, the common oxidation numbers for titanium, it's +3 and +4. For vanadium, it can form +2, +3, +4, because the more it can remove electrons, it can remove electrons. Titanium has 22 electrons, and the electronic configuration for titanium is argon, 4s2, and 3d2. So if you look at titanium, it can remove these 2 electrons and form +2. It can remove 2 electrons from the 4s and only 1 from the 3d, and it forms the +3. These are the most common, but this doesn't mean that it doesn't form +2. It can form +2, but the most common oxidation numbers are the +3, where 2 electrons are removed from the 4s and 1 electron from the 3d, or else it forms +4, where it can remove the 4 electrons present in the 4s and the 3d. When we come to vanadium, that is below it, it has 3d3, 4s2. You see, it can remove these 2 electrons and can remove these 2 electrons and 1 from the 3d to form the +3. It can remove 2 from here and 2 from the 3d to form +4. It can remove all the electrons to form +5. The chromium can form up till +6. The manganese up till +7, because manganese has the electronic configuration. Manganese 25, it will be argon 3d5 4s2. So it can remove starting from 2 till +7, where all the electrons are removed. It can form all of these, but these are the most common oxidation numbers. When we look at iron, it can form +2 and +3 only. When we look at cobalt, it forms +2 and +3, nickel +2, and copper +1 and +2. No, Abdurrahman, you don't have. No. Abdurrahman is asking me, can we, do we have to memorize these? No, you don't have to memorize them. No. Okay. Now, if you look at these oxidation numbers, you will see that the higher oxidation numbers, +5, +6, +7, they are usually where the metal ions are bonded to oxygens as well. You see V2O5, you see K2CrO4. The higher oxidation numbers are usually where the metal is bonded to oxygen. It is usually in that case. Now, when we look at these elements that are present from titanium to manganese, this means that up till +7, it can form positive ions up till +7 and share in forming bonds. But if you look from iron downward, you will see that only the positive charges that are small are the only one present as ions. And that's because as we go down, or as we go from titanium to copper, you will see that the nuclear charge increases. If you remember what is the nuclear charge, it is the charge divided. Yeah, it depends on the charge and the size. You will see that for iron, cobalt, nickel, and copper, as we move from titanium to copper, you will see that the size becomes smaller and the mass becomes bigger. So when the mass becomes bigger and the mass and the size becomes smaller, it will have higher nuclear charge. And the more the nuclear charge, the more the electrons will be attracted to the nucleus, and that's why they do not leave. They do not want to leave. That's why iron, cobalt, and nickel, they do not form more ions than +2 or +3, because the nuclear charge increases and the electrons are more attracted to the nucleus, and they do not want to leave the nucleus to form other compounds or to form other bonds. Understand me? Do you have any question here? Any question? Okay. Yes. What is the last sentence I said? I said that, yes, okay. Okay, Yajuman. I said that as starting from iron, you will see that the ions that are formed are only +2 and +3, not more, like in case of manganese or chromium. Why? This is because starting from iron and cobalt, nickel, you will see that the nuclear charge increases as there will be more positive charge or more positive protons inside the nucleus, and the size becomes smaller and smaller, which means that the nuclear charge increases and the outer electrons will be attracted towards the nucleus more than the others. That's why the electrons would not like to leave the atom to form more ions, more than +2 or +3. Okay. Now we look at something that only transition metals can form, which are complexes. You're welcome, Joanne. We look at something that only transition metals can form, which are the complexes. Now, what are complexes? Now, when we studied before about the dissolving of, for example, sodium chloride salt, when we studied this in the AS, we've seen that when you place sodium chloride in water, it dissolves. And what is dissolving means? It means that the water molecules separate between the sodium ions and the chloride ions, and they surround the sodium ions using their partial negative oxygen, and they surround the water molecules, surround the chloride ions using the partial positive charge of the hydrogens. And we say that there is an ion dipole bond that is formed. An ion dipole bond forms between the sodium ions and water, and between the chloride ions and water. Okay, now something similar to that happens with transition metals, but because transition metals are smaller in radii, smaller in radius, so they will attract more electrons towards the ion. For example, if we have an iron plus 2, of course, it is iron plus 2. So since the iron plus 2 has a small radius, it will attract, we studied in unit 4 that when the ion has a big charge and small radius, it will attract more electrons. You remember the delta H of the solution or the delta H of hydration? We said that the smaller the ion, the more the water molecules will be attracted to this ion. So that's what happens here. When the iron, since it has a small radius, then it will attract the water molecules to it. Usually, when water molecules are attracted to transition metals, 6 of them surrounds the metal ion. Usually, when we place any transition metal ion in water, of course, we don't place the ion, we put the salt. But for example, if I have iron sulfate, when it is placed in water, then this means that it will be ionized into iron plus 2 and sulfate ion. We are not going to talk about the sulfate ion. We are going to talk about the iron plus 2. Since the iron plus 2 has a small radius, it will attract water molecules around it. And usually, when water is attracted to any metal ion, it is at 6 molecules of it are attracted to the metal ion. Okay, and in that case, what happens? Here we said that we have an ion dipole bond formed between sodium and water, or chloride and water. But in case of transition metals, what happens? When a transition metal is surrounded by water, when a transition metal is surrounded by water, usually, as we said, 6 water molecules are going to surround the metal ion. We will see that, for example, if we are taking iron as example, but of course, this will happen for the others as well. We will see that 6 water molecules are going to be attracted to the iron. But what happens here is that the water will form a dative bond. The water will form a dative bond between itself and the metal ion. If you remember, what is the dative bond? Does anyone know what's the dative bond? Abdelrazak, how are you? What is meant by the dative bond, ya Abdelrazak? Yes. Do you remember, ya Abdelrazak, what is the dative bond? Yes. Okay, Abdul. Yes, excellent. Yes, ya Abdelrazak, excellent. Abdelrazak said a bond where an element shares 2 electrons with another element. Excellent. A dative bond, when you have an element that has a long pair of electrons, it can share these 2 pairs of electrons in a covalent bond with another atom. For example, here, when we said that water, for example, when it reacts with hydrogen ions, we said that here it will form what we call the hydronium ion. The hydronium ion, where the electron shares 2 pairs of electrons. Yes, excellent, ya Basma. So here the water has a lone pair of electrons and hydrogen ion has deficiency of electrons. It has no electrons. So a dative bond is formed between the water and the hydrogen ions. It is a normal covalent bond, but the only difference is that the lone pair of electrons comes from one element and the other element does not share by any electron. This is the difference between a normal covalent bond and a dative bond. So here when water surrounds the iron ion, of course, then water will do the same. It will form a dative bond with the iron. And usually when we draw an arrow, it shows that the electrons are shared from the oxygen to the iron. And the iron will not share by any electron. So here when the water surrounds the iron, it will form a dative bond, 6 dative bonds with the iron. Yes, of course, Yegehet, of course. And so the water will form a dative bond with iron. But as we said that usually since iron is a small ion, it is a small ion, so it will attract 6 electrons. Usually when water is attracted to metal ions, 6 of them surrounds the metal ion. And here we have to draw a bracket to show that the iron still has the +2 charge since the water molecules are neutral. So the positive charge that was on the iron is still present, but we draw a bracket and we write +2. Now, if you look at this structure, you will see that we have to draw water in this way. We have to show that the oxygen is the one that formed the dative bond with iron, because sometimes when they ask you to draw the structure of a complex, some of the students would draw like this. This is wrong. If you draw like this, this is wrong. Why? Because here you show that hydrogen is the one that is bonding to the iron and not the oxygen. You have to show that the oxygen is the one that is sharing its electrons with the iron, not the hydrogen. If you write the water in this way, this is wrong. You have to write oxygen in front of the arrow, not the hydrogen. That's why we write OH2, OH2, to show that it's the oxygen that is forming the dative bond with iron. Okay, now also, if we want to show it in the 3 dimensions, because sometimes they ask you to draw it in the 3 dimensions, then we have to draw it in this way. We write iron. So this is the 6 water. We draw wedges like this. We draw 2 wedges and we draw here the dotted lines to show that we have, of course, those water molecules that are at the same solid line with iron. It means that these 2 water together with the iron are present in the same plane. And then we have 2 water molecules outside the plane, behind the plane of the molecule. And these 2 wedges means that these 2 water molecules are in front of the plane. These are in front and these are behind the plane. And this is the plane. Okay, so if they ask you to draw a 3-dimensional structure, you have to show the wedges and you have to show the dotted lines. Okay, now as we see here, that as we said, that water formed dative bonds with the metal ion, and that 6 of the water molecules are formed around the iron. Not only the iron, but any metal ion surrounded by water molecules, we should draw it in this way. 6 water molecules. Okay, now we call this a complex. We call this structure that I have drawn now, we call it a complex. Now, what is a complex? A complex is when a metal ion bond with something called a ligand, it forms the complex. Now, the metal ion in our previous example is iron +2. The ligand is the water. And the complex is this complex formed. Of course, not every time we are going to draw this structure, because we are going to see in the second part of the chapter that we are going to take equations. So of course, we are not going to write this structure, this big structure. So we are going to write a complex in this way, iron, sorry. Yes, yes. I put +2 because the iron at the beginning, where is it? Because the iron at the beginning had the +2. Okay, so we say here metal ion. They are not metals, they are ions that are forming the dative bonds with the ligands. They are called metal ions, not the metal itself. And it forms the complex where we can draw the complex in this way. Instead of drawing it in the big structure, we just draw it in this way. So whenever a ligand reacts with a metal ion, it forms what we call a complex, and this doesn't happen except with transition metals. A ligand reacting with a metal ion forming a complex. Now, what is a ligand? A ligand is any species that has a lone pair of electrons, and form a dative bond with a metal ion, So this is the ligand. What is a ligand? A ligand is any species that has a lone pair of electrons and form a dative bond with the metal ion, just as we said with water, as we have seen with water. So is only water is the only ligand present? Of course not. We have a lot of ligands, and from them we are going to study, for example, water is a ligand, ammonia is a ligand, hydroxide ions are ligands, cyanide ions are ligands. Okay, anything. Of course, we are going to take more. Chloride, of course, the chloride ion is a ligand. Okay, so whenever we have any species, we said the species because it could be neutral, like water and ammonia. They are neutral, they do not possess any charge, or they are negatively charged, we call them ligands. Whether they are neutral or they possess a negative charge, they are ligands. Why? Because they have the lone pair of electrons that can form dative bonds with metal ions. And of course, metal ions means copper ions, cobalt, nickel, iron, whatever. All the transition metal ions can form complexes with ligands. So when a metal, this means that this is a complex. We call this a complex, where the water molecules formed dative bonds with iron. It forms what we call a complex. We can have a charged complex like this one. It has a positive charge. It could be a negative charge as well, and it could be a neutral complex. Okay. Do you have any question till here? So if you look here in the table, in the book, you will see that we have different ligands. We have water, but water, of course, as I told you, it's neutral. But when we name water in complexes, we call it aqua. We are going to say aqua. Hydroxide ion has a negative charge. When we name it in the ligand, as a ligand, we are going to call it hydroxo. Aqua, hydroxo. Ammonia is going to be named amine. This amine has a double M. It is different than the amines that we are going to study in organic chemistry, where we have an NH2. This is called amine with one M. But here, amine with double M. They are pronounced the same, but here we write it ammonia, we write it amine having double M. Chloride, carrying a negative charge, we are going to call it chloro. Okay. So if we want to name the complexes, so here, for example, when we have iron, H2O6 + 2, we want to name this complex. So here we start by naming the ligand first. We start by giving the number of ligands that are present. We say, of course, we know that 6 means hexa, so we say hexa. And we said that water is going to be called aqua, so we say hexa aqua. And then we write iron, sorry, and we put the charge of the ion between brackets in Roman letters. So we say hexa aqua iron 2. Here, because the complex has a positive charge, we say iron 2. Now, if we look at the second one, FeCl4 negative, you see here there is a negative charge on the complex, not a positive one. Also, we start with the ligand. We say tetra. We know that 4 means tetra. Tetra chloro. When we have a chlorine, we say chloro. Tetrachloro. Now, for the iron, we do not say by iron 2. Why? Because the complex here carries a negative charge. So we say ferrate. Ferrate 2. Here, of course, we have 4 chlorides by negative 4. So the iron is plus 2. So we say ferrate. You know that iron, the symbol of iron is Fe, which comes from the Latin name ferrum. You know, of course, maybe you studied this, maybe when you were at grade 7 or 8, they tell you that, for example, sodium is called natrium in Latin. That's why they give it the symbol Na. Potassium means kalium, so that's why they give it the symbol K. Also, iron is called ferrum. That's why they give it the symbol Fe. So here we call, since the complex has a negative charge, we are not going to call it iron as we did here. We say iron if it's positive. If the complex as a whole is positive, we say iron. But if it is negative, we put ATE at the end. Ferrate, and then 2 between brackets. Okay. If you come at the last one here, we have 2 ligands. We have ammonia and we have water. So we start with the one alphabetically is before the other. So amine is before aqua. The letter M comes before the letter Q. So that's why we start with the amine. We say tetraamine. Di, because we have 2 water, we say di aqua. And then we say copper between brackets 2. You will see that yani, they don't ask about naming complexes in exams. I didn't see it at any exam, but it's present in your syllabus that you have to know how to name complexes, but I never saw any question asking about naming of complexes. But we have to know it because it's present in your syllabus. Okay. Do you have any question till now? Type. Okay. What were you asking about? The charge 2 gives the 2. Yes. Yes. If you have a charge plus 2, this means that you write 2. Here, if you count for the oxidation number of iron, you have 4 chlorine, each with -1. So -1 times 4 makes -4. And since the charge is at -1, so this means, here it's 3. Here the charge on the iron is +3, not +2. Because you have, so here we should put here 3. Yes. Yes, excellent. Thank you so much. Okay. Do you have any question, Gama? Of course, Bisan. تفضل.
Thank you, Miss. مع السلامة.
You're welcome. مع السلامة, Bisan. Why 3, ya Jumana? Because if you count here, you see that if I put here iron, if you put iron, Cl4, you know that the oxidation number for chlorine is -1, and you have 4 chlorines, so it's plus times 4 makes minus 4. And the total charge is negative 1, which means that iron is plus 3, because when you add plus 3 minus 4, you get minus 1. So this means that the charge on the iron is plus 3, not plus 2, in case of FeCl4 minus. Understand it, or shall I repeat? تمام، اوكي. جماعة، في حد عنده أي سؤال لغاية دلوقتي؟ لو سمحتوا، لو في أي حد عنده أي سؤال. Any question؟ خلاص عرفنا يعني what is meant by a complex، عرفنا what is meant by a ligand, how complexes are formed. Okay, تمام. Now, one of the properties of transition metal complexes is the colors. You will see that all the salts of transition metals are colored, whereas any other salt is white. If you have sodium sulfate, it is white. If you have magnesium carbonate, it is white. If you have anything, any calcium sulfate, calcium chloride, all these are white in color. The only colored compounds and complexes are those of the transition metals. Now, why the transition metals are colored? Of course, not the metals themselves. I don't mean the metals. I mean the compounds of transition metals. Of course, the metals are not colored, except copper is the only colored one, which has, we say, a pinkish brown color or a brown color. But I mean the compounds of the transition metals. You will see that copper compounds are usually blue. Some of them are green, but they are usually blue. We will see that, for example, those of nickel are usually green. Those of iron plus 3 are reddish brown. So all of the complexes are colored. All the transition metal complexes are colored. So why the transition metal compounds are colored? In order to study about colors, we have to know that the white light, we say that the white light is consists of electromagnetic spectrum. Of course, you studied this, I think, in physics. We know that light is divided into more than one type depending on its energy. Not all the light has the same energy. We have, as you know, we have radio frequency. We studied about NMR, nuclear magnetic resonance. We know that nuclear magnetic resonance, we use radio frequency. We have microwaves. We have infrared. Yes, Jihad, we have infrared. Then we have here, I'm going to draw it in a big size, but it's the least one of them. Yes, Jihad, the visible light. We have here the visible light at which we see colors, and we have here the ultraviolet, we have the gamma radiation, and we have the X-ray and then the gamma. Yes, X-ray and then gamma. Okay, and we know that as we go from right to left, the energy of light increases, energy increases, and as we go from left to right, the wavelength of the light increases. We call it lambda. I don't know if you studied about this or not, and it doesn't matter. For us, it doesn't matter. Now, we are concerned with this part, which is the visible light at which we can see colors. So if we take this visible light and we enlarge it, we will see that beside the infrared, we have the red color, and then we have the orange, we have the yellow, we have the green, and then the blue, indigo, and at last we have violet that is near to the ultraviolet. Okay, of course, these are not distinct colors like that. We have hues. What do we mean by hues? It means that in between we have different colors. Yeah, between red and orange we have different colors, dark red and then bright red, and then mixed between red and orange, but then mixed between orange and yellow. So we have different colors but these are the main colors that we have. Now, if we join the red color with the violet color, we get what we call the color wheel. If we are going to connect the red color with the violet color, the one at the most right-hand side to the one that is at the most left-hand side. Of course, they have drawn it in an opposite direction that I did. I started with the red and ended with the violet. They did the opposite. You see here we have hues of colors. If you connect, as if you took this end and you connect them together, we get what we call a color wheel. You connected the red light with the violet light. We said that red, we have orange, yellow, green, blue, indigo, and violet. So if you connect these two ends together, we get what we call a color wheel. Now, what happens? If you put a solution containing your transition metal solution, the transition metal compound solution, you put it, for example, in a beaker and you subject it to the white light, which is our normal light, then we will see that the compound here, or the complex, is going to absorb a certain color, or it absorbs more than one color. And here, some of the light at which it was subjected is absorbed. It absorbs light, and the others are going to be transmitted. Transmitted means that it will leave without being absorbed. So when you subject your solution, which contains a transition metal ion, you subject this solution to white light, you will see that your solution is going to absorb colors from the white light, and others are transmitted. It means that they are not absorbed. We see this transmitted light. Okay, so if our solution absorbed the red color, then the solution will appear for us either blue or green, because when we do this color wheel, we say that every color has a complementary color. Every color has a complementary color. So if the solution absorbs, for example, the red color, we see the complementary. The complementary that is transmitted here is either the blue color or the green color. And of course, the opposite. If a solution absorbs, for example, the blue color, it will appear red. If a solution absorbs the orange color, it will appear indigo. If it absorbs the yellow color, it will appear violet, and so on. So you will see that we have different colors for the different transition metal ions, of course, present in their compounds. We have all the colors because it depends on which color is absorbed and which one will appear for us. If it is red in color, as this one, for example, or that one, this means that the solution absorbed either the blue or the green color. And if the blue color appears, this means that the solution absorbed the red one, and so on. We call them the complementary colors. We see the complementary colors of what was absorbed. Okay, understand me? Do you have any question till here? Okay, now why these complex ions absorbs colors? What happens, Yan? What happens, and why do we see the colors? Now, we know that transition metals, we said that they have d electrons. We are going to talk colors of complexes. Now, for any transition metal, its electrons are filling the d orbitals. And we know that we have 5d orbitals. And the 5d orbitals, all of them have the same energy. All the 5d orbitals have the same energy. Let us take, for example, a copper ion. This is the one that we are going to talk about. If we have a copper ion, then as we said that there are 9 electrons present in the copper +2. We have 9 electrons in the d subshell. And this means that all the d subshell all have the same energy. And we have 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 electrons in the copper ion. Now, what happens when water starts to approach the copper ions in order to form the complex? We said that all the metal ions, all the transition metal ions, when they are placed in water, the water is going to surround them from 6 places, like this, to form the complex ion. Okay, so what happens when water, of course, all of these are water. Now, what happens when water approaches the metal ion in order to form the complex? We will see that these 5d orbitals are going to split. The 5d orbitals here, they all have the same energy. All of them have the same energy. That's why we draw them all in the same level. But as the water ligands approach the metal ion, the d orbitals start to split. The d orbitals split. They split into 2 energy levels. We will see that we have here 2 energy levels. One of them containing 3d subshell, and the other will have a higher energy, having 2d subshells. This happens when the water ligand, or any ligand, but we are taking water here as an example. But if any ligand start to approach the metal ion, we will see that the d orbitals are going to be split into 2 different energy shells. One of them containing 3 of these d orbitals, and the other contains 2. And now we have these electrons: 1, 2, 3, 4, 5, 6, 7, 8, 9. So here there is an empty space. There is an empty place, I mean. Okay, I'm going to repeat this. How colors arises in metal ion complexes, of course, of transition metal ion complexes. How colors arises. Now, we said that for any metal ion, which is a transition metal ion, and we are going to take copper as an example, it is, of course, copper +2. It means that an electron from the 4s is removed and another electron from the 3d is removed. So the electrons are arranged in this way: 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, now what happens as the water molecules approach the copper ion? We will see that these d orbitals are no more having, all of them having the same energy, but they are going to split into 2 different energy levels. One of them containing 3d orbitals, and the other contains 2d orbitals. And the electrons are arranged in this way. Do you have any question here? Any question? Okay. Now, what happens when we subject our compound to light? It is subjected to light energy. Okay, Jumana is asking why it is split into two upward d orbitals and 3 downward. Okay, this is, yani, I can of course explain it to you, but it's not in your syllabus. Yani, Cambridge, they study this. They study why they are split into 3 lower energy shells and or orbitals and 2 upper one, but it's not in your syllabus. I can explain it to you, but it will take time and it's not in your syllabus. All you have to know is that they are split into 3 lower energy orbitals and 2 upper. But if you'd like me to to explain it to you, I can do it, yani, between me and you in another time, because Cambridge studied this, but you don't. Okay. Okay. So all you have to know is that when the ligands, because this question comes a lot in exams. Explain the origin of colors in transition metal complexes. It comes a lot in exams. So you have to say that before the ligand approach the metal ion has 5 d orbitals, all having the same energy. But as the ligand approaches the metal ion, the d orbitals are split into 3 lower energy orbitals and 2 higher. We call this the ground state. Sometimes we call it the ground state. If you'd like to, we call this the ground state, and we call the upper one the excited state. You can call it like this, or you don't. You can only say 3 lower and 2 upper, or you can say 3 ground state and 2 excited states. Now, what happens when we subject this complex or this solution of the copper ions into light? What happens when light is subjected to this metal ion? We will find that the lower electrons, one of these lower electrons, will absorb the light that is given to it, and is going to be, we say, promoted or excited from the lower energy shell to the higher energy shell. Either we say promoted or we say excited. When the electron absorbs light, it is either promoted or excited from the lower energy shell to a higher energy shell. And when it absorbs this amount of light, then we see the complementary color. We see the complementary color, which is the color that is transmitted, that was not absorbed by the light. Okay, I'm going to repeat this. We said before that, if we look at the book here, we said that we have different colors for different complexes. Now, what is the origin of all these colors? Is that when a solution of the transition metal complex is subjected to light energy, so part of the light is absorbed by the solution and another part of light is going to be transmitted. The transmitted light, we call it the complementary color. Complementary color. The solution absorbs a certain color. The solution absorbs a certain color, and the complementary color is the one that is transmitted. We see this complementary color. From where will we know the complementary color? From the color wheel. We said that if these solutions are subjected to light, because we are going, of course, we cannot see the colors in the dark. If you take this solution and put it in the dark, you will not see any color. But if it is present in the light, so it will absorb this one. It absorbed, for example, the red color that is present in the white light, and so it appeared blue. It appeared blue because it absorbed the red color. And what we see is the transmitted light. We call it the complementary color, is the color that we see. Now, what happened here inside the solution for any metal ion of these is that we said that for any metal ion, the electrons are present in the d subshell. We are going to take copper ions as an example. It has 9 d electrons. And so when the water ligands or any ligand, as we are going to study afterwards, we can use any ligand. But of course, for this example, we are going to use water. When water or any ligand approaches the metal ion, then these 5 d orbitals are no more having the same energy, but they are going to split. We have to say this word. Then the energy levels are going to split into 2 energy levels, a lower energy level, which we call the ground state, and a higher energy level, which we call excited state. If you do not want to say ground state and excited state, it's okay. You can say only that the energy levels are split into 3 lower energy levels and 2 higher energy levels. And when we subject this solution to white light, the electrons in the ground state or in the lower energy level will absorb this light and it's going to be promoted or excited to a higher energy shell. And on doing so, when it absorbs, the transmitted light, which is the complementary color, is seen. That's all you have to say about this part. Do you have any question here? Do you have any question till here? Yes, Abdurrahman, yes. Yes, but in the flame test, we say, Abdurrahman is asking, is this the same way as in the flame test? Yes, it's the same way, exactly. But what we say in the flame test, we say that when the electrons are, excited to a higher energy shell, when they return, we see the emitted light. That's what we say in the flame test, isn't it? In the flame test, we say that when electrons absorb the heat energy, electrons are excited to a higher energy shell, and then when they return back, they emit light that we see in the flame test, isn't it? So that's the only difference, that in the flame test, we say when the electrons return back to their position, they emit light that we see, they emit colors that we see. But here we don't say so. Here we say when the electrons absorb light, they are promoted or transferred or excited to a higher energy shell, and we don't say that the electrons are going to return back. No, we say that, and we see the complementary color. Okay. Do you have any question here up till now, Yani? Type. Okay. Type. We have two questions here. Why different colors appear for different complexes? You're welcome, Abdurrahman. So we say that why different complexes have different colors, and why zinc is not colored? Why is it white? Although it has electrons in the D subshell, but it's white. Now, let's take the first question. The first question says, why different complexes have different colors? Why copper is blue? The copper complexes are blue. The iron +2 complexes are green. The iron +3 complexes are reddish brown. For example, the cobalt complexes, some are pink and some are blue. Why? Why do we have different colors for complexes? We have two reasons for the colors. The first reason, both reasons depend on this energy. We call it energy gap, or difference in energy between the lower ground state and the higher excited state. So, of course, it depends, the colors depends on two factors. Different colors depend on two factors. They depend on the type of ligand and they depend on the charge on the metal ion. They depend on the type of ligand and they depend on the charge on the metal ion. We said that at the beginning we had 5 d orbitals all having the same energy, and they split it into 2 energy levels. Now, if the ligand is a weak ligand, it will split these 2 energy shells with a small energy difference. The difference between them is not so high. And so when the electron that is present here absorbs light, it needs only to absorb light with a small amount of energy in order to be excited or to be promoted to the higher energy shell, because the difference between these 2 energy shells is small. It is a small difference. So the electron doesn't need a very big energy in order to be excited to this place or to be excited to a higher energy shell. It needs only energy with a small amount. So as we said here, if I'm drawing, this is the, if this is the red color, This is the orange, the yellow, and so on. Now, as we go in this way, the energy increases. It means that if the difference in energy between the ground state and the excited state, or we say the lower energy shell and the higher energy shell, if the difference is not so high, it's not so big, then only the electron can only absorb the red color, for example, which has a low energy, in order to be promoted or excited from the ground state to the excited state. It needs only a small energy. But if we have a strong ligand, then the splitting will be higher, will be bigger. You see? So the electron here, in order to be excited or to be promoted to a higher energy shell, it needs a higher energy. So maybe it will absorb in the blue region. No, they absorb the red, and so they will appear, it will absorb the red color and it will appear blue or green, isn't it? Depending on the color wheel, ya Juman. If it absorbs the red color, which has a small energy, then it will appear either blue or green, depending on the wheel color. Understand, ya Jumana, or shall I repeat this? Jumana, do you understand, or shall I repeat? Okay, so we see the complementary color. We don't see the absorbed color. Okay, some ligands, we call them strong ligands, and others we call them weak ligands. And also you do not have to know which one of them is a strong and which one is a weak. The strong one will make this splitting to be having a big difference. Whenever we have a strong ligand, the strong ligand will affect this splitting so high, by a big difference. But if you have a weak ligand, the weak ligand will split the energy levels of the d orbitals into a smaller difference between them. That's the difference between a strong ligand and a weak ligand. And of course, you don't have to know which ligands are weak and which ligands are strong. But for example, the cyanide ligands are very strong. The cyanide ligands are very strong. The water ligands are in between. They are not very weak and they are not very strong. If you have a chloride ligand, it's a weak, but you don't have to know that. That's why I didn't mention them. But if you have a strong ligand, what is meant by a strong ligand? A strong ligand will affect this splitting by a big difference. It will split the d orbitals, having a big difference between them. But a weak ligand will split them also, but by a small difference. Okay, Abdurrahman? So if we have a strong ligand that affected this splitting by a big difference, okay, you're welcome. This means that this electron has to absorb a high energy light in order to be promoted from the ground state to the excited state. It would have, for example, to absorb the blue color. And in that case, it will appear red. If it absorbs the blue color, which has a high energy, then the color of the complex will appear red, for example. If it absorbs, for example, a violet color, because the difference was so high or so big, it could absorb the violet color, and in that case, it will appear yellow, depending on the wheel color. Okay, but if the ligand was a weak one, and the difference between the splitted energies is not so big, this means that it was a small difference. This means that this electron needs only a small amount of energy in order to be excited or in order to be promoted from the lower energy shell to the higher one, which means that it can absorb, for example, in the red region. And at that time, it will have the blue color, because we see not the color absorbed, we see the color that is transmitted, or we call it the complementary color. Also, what affects the difference between these two energy levels could be the charge. If you have a metal having a +2 charge, is different than if you have it having a +3. The +3 would also affect the difference in splitting between the lower and the higher energy shell. So we have two things affecting the splitting of the energy shells, the type of the ligand and the charge on the metal ion. Understand, or do you have any question to ask? The colors, of course, yani comes a lot in exams. It's not hard. Yani all you have to say is that as the ligand approaches the metal ion, it's going to split the d orbitals into 3 lower energy orbitals and 3 energy levels, and it is going to split the d orbitals into a lower energy level and a higher energy one. And as the electron absorbs the light energy, it's going to be promoted or excited from the ground state or from the lower energy levels to the higher ones. And on doing so, the complementary color appears. That's all you have to say. Okay, do you have any question? Yes, yes, Abdurrahman. If you have the metal ion having a higher charge, it will split. It will have a bigger difference between the energy shells more than if it has a lower positive ion. Okay. Now, the second question that we said, why do, for example, zinc compounds, of course, we said that zinc is not a transition metal, but they can ask you why zinc compounds are white. So if we are talking about transition metals, why copper 1 compounds are white? Those who are colored for copper are the copper 2. When we say copper sulfate, when we say copper chloride, all these, the copper present here has a +2 charge. But we have, as we've seen, we have copper present as copper +1. Why copper +1 complexes are white? And why zinc ions are white? Now, we said that if we write the electronic configuration of zinc ions, it would be argon and then 3d10, because the 2 electrons that were lost from the 4s2. And also, if you have copper +1, this means that the electronic configuration is also argon 3d10, because the electron that is lost from the 4s1, isn't it? So in both cases, we have 3d10, even if the energy levels or the orbitals are splitted into a higher energy shell and a lower one. Now we have 10 electrons. So there is no space for any electron to be excited or to be promoted from the lower energy level to the upper one. Here we had a space here. When we talked about copper, you see, there is a space here left. All the electrons are paired, but here we have a space for an electron to be excited from the ground state to the excited state, or to be promoted from the ground state to the excited state. But in case of the zinc and the copper +1, there is no space. Even if this electron will absorb light energy, it will not have any space in order that it can be promoted upward. So the electrons are not moving, and that's why it will appear white, because it is the promotion of an electron from the ground state to the excited state by the absorption of light energy that shows us the colors. Okay. Any question till here? Now, when we were talking about yes, no light is absorbed nor light is transmitted. Yes, Abdurrahman. Nothing happens because the electrons have no place to go, so they are not going to absorb the light. Okay. Now, when we talked about, yes, thank you so much. When we talked about such complexes at the beginning, I didn't tell you that the number of bonds between the metal ion and the ligands, we call it the coordination number. We call this the coordination number. What is the coordination number? It is the number of bonds, of dative bonds, of course, between the metal ion and the ligands. The number of bonds here, the coordination number here is 6, because there are 6 ligands forming 6 bonds with the iron. We call this number of bonds, we call it coordination number. Now, as we said, we have different types of ligands, and also we have different shapes of complexes. You remember, of course, when we were studying in the AS, I don't know if you remember or not, but if you do remember, we studied about the shapes of compounds, and we said that there is a theory that is called the valence shell electron pair repulsion theory. You remember this theory that stated that the shapes of the compounds depends on the repulsion between the bonding pairs of electrons, and as bonding pairs of electrons repel each other, they behave in such a way they have maximum separation to make the repulsion between them in the minimum. You remember the Vesper theory, the shapes of compounds? We said that, for example, if a metal like beryllium chloride if the metal beryllium is bonded to 2 chlorine, then it is bonded by 2 bonding pairs of electrons. The chlorine atoms take this shape, which is the linear shape, so as to minimize the repulsion between them. So they will have this shape to have maximum separation. If we have boron trichloride, we have the trigonal planar structure. You remember such things? If we have something like methane, we have the tetrahedral shape. All these shapes are due to the separation or due to the repulsion between the bonding pairs of electrons. If we have, for example, SF6, we have the tetrahedral structure. You remember that? So also the shapes of complexes depends on this theory, depends on the Vesper theory, the valence shell electron pair repulsion theory. As we have seen that when iron was bonded to 6 water ligands, then it takes the octahedral shape. It takes the octahedral shape because here we have 6 bonding pairs of electrons from the water to the iron. We have 6 bonding pairs of electrons. Of course, here we have to put the 2 positive. We have 6 bonding pairs of electrons, and in order that we have maximum separation between these bonding pairs of electrons to have minimum repulsion, the bonding pairs will take the shape of an octahedral. Exactly like here, like in SF6, it takes the shape of an octahedral. Okay, and of course, as we said here, the angles are also, do you remember, Yasara? What is the value of the angles in the octahedral? Yes?
Was it 107?
No, in octahedral. You see, in octahedral, we have this shape. The metal ion or the sulfur in the middle, we have 6 fluorines at the corners, and then 1 fluorine upward and another downward. So what were the angles? Yes, excellent, Abdelrazak. Excellent. They are 90 degrees, isn't it? They are 90 degrees and 180. Yes, Yejoman. Between these 180, and between every sulfur, fluorine, sulfur, fluorine is 90 degrees, isn't it? They are present at the corners of a square. Yes, yes, Sarah?
Yes, miss, yeah.
So here the same. As long as we have an octahedral shape, so the angles are 90 degrees between OH2 iron and OH2, because these lie on a plane, and we have a water molecule above the plane and another water molecule below the plane. So all the angles are 90, or we can say 180 between this water, iron, and this water. We have 180, or between any two water and iron, we have 180 degrees, isn't it? Okay, what if we have something like that? Copper Cl4 minus 2. If we have copper Cl4 minus 2, this means that copper is surrounded by how many chlorine, ya Abdelaziz? Copper is surrounded by how many chlorine atoms? Yes, Abdelaziz. The copper is surrounded by how many chlorines? Yes, excellent. They are 4. And when there are 4 around the copper, what shape does it take? Basma, what shape does it take? When we had CH4, the central atom is surrounded by 4 other atoms. What shape did we take? Yes, excellent, Yejuman. Yes, ya Basma. What is the shape of methane? Yes, excellent, ya Basma. It is tetrahedral. Tetra means 4, tetrahedral. So here also, when copper is surrounded by 4 chlorine atoms forming this complex, then it will have also the tetrahedral shape. The tetrahedral shape, and the angles here will be, do you remember, ya Geher? What is the angles between chlorine, copper, chlorine in a tetrahedral shape? Yes. Yes, excellent, Amina. Excellent, Gehed. No, Gehed, it's not 90. No, Amina, excellent, and Basma, excellent. Yes. So as Basma and Amina said, it's going to be, I don't know what's happening. It's going to be 109.5 degrees. It's not 90 because it's not a square. It is a tetrahedral. It's not a square to be 90. So it's 109.5, isn't it? But sometimes we have, for example, for silver, we have, you studied about Tollens reagent. All of you know Tollens reagent, isn't it? Of course, there are lone pairs, of course, but you should, yani, when you draw it quickly, you don't have to show them. But of course, if they ask you to draw it, you have to draw the lone pairs, of course. On copper, no. Copper at the beginning had a +2, isn't it? But when it was surrounded by 4 chlorine atoms, so every chlorine having -1 times 4 makes -4. And since copper at the beginning had a +2, so the total charge on the complex will be -2. You don't have lone pairs on copper because it's an ion. You don't have lone pairs. Lone pairs are for ligands only. Okay, Abdurrahman? Okay, now you heard about Tollens reagent, isn't it? Thank you so much. You heard about Tollens reagent. Do you remember, ya Muhammad Tahir, what is Tollens reagent?
Yes, doctor.
Yes, what is it?
But I don't remember the exact chemical name.
Okay, but you know about Tollens reagent. Okay.
Yes.
Okay, Karim, do you remember what is Tollens reagent? Salim, what is Tollens reagent?
لسه مش فاكر بالظبط.
مش فاكر. اوكي. طيب ياسين فاكر تولنز ريجن؟
لا بصراحة.
لا حول
آه،
الله، ذاكرتكم
is it
ضعيفة ليه كده يا
silver-
اولاد؟ ما هتعملوا ايه لما تبقوا قدي؟ ها؟
is it
تعملوا ايه
silver
لما تبقوا قدي؟
nitrate?
ياسين محمد كنت بتقول ايه؟
I'm asking if it's silver nitrate.
Yes, silver, but it's not silver nitrate exactly. It is what? Yes, يا أبرار. It is a test for aldehydes. Yes. What was its structure? Yes, يا كريم. Yes, you remember that it is a test for aldehydes. You remember that it is used to this. You mean not to separate you. It means to distinguish between aldehydes and ketones, not to separate, isn't it? So, what did we call it? We call it ammoniacal silver nitrate, didn't we? Misk, do you know what is its structure, yeah, Misk? Tollens reagent?
I'm not sure.
You're not sure. Yes, يا عبد الله. أرجوك انقذني. Yes, يا عبد الله.
Miss AgNH3
Excellent.
2
AgNH3, but what يا عبد الله?
في 2 on the NH3
كده؟
all 2.
وعليها positive charge, isn't it?
Yes.
We call it ammoniacal. Excellent, يا عبد الله. We call it ammoniacal silver nitrate. Ammoniacal means that there was ammonia inside the silver nitrate. And we are going, of course, when we study, inshallah, next time, the reactions, we are going to see it once more. Silver, ammoniacal silver nitrate. It means that ammonia here is acting as a ligand with the silver. The silver is a metal ion. It's a transition metal ion. And ammonia is acting as a ligand. But since we have only 2 ligands around the silver, it is exactly like when we talked about beryllium dichloride. This means that 2 ammonia molecules are acting as ligands with the silver, and we get, of course, ammonia is neutral. Of course, it forms the dative bonds with silver, and so it has a linear shape. So shapes of complexes are like the shapes of other compounds. They are controlled by the VSEPR theory, which is the valence shell electron pair repulsion theory. Okay, so if you look here at different shapes of complexes, we see that if the coordination number or the number of ligands is 6, they will donate 6 electron pairs. 6 electron pairs. So the shape will be octahedral, and we say that the bond angle is 90. An example is cobalt NH36 plus 2. We don't have always to say water. Here we have our ligand is ammonia. So cobalt is surrounded by 6 ammonia ligands. We have 6 ammonia ligands. As you see, we always draw the atom that will donate the electrons to the cobalt. And since cobalt has a +2 charge, and since ammonia is neutral, we draw it in this way. Of course, if they want us to draw in the 3 dimensions, we have to show the wedges, and we have to show the dotted lines. So here, the shape here is octahedral, which is cobalt. Of course, we call this hexaamine cobalt 2. If you want to name it, we say hexaamine cobalt 2 between brackets. Like an example of ordinary molecules or simple molecules, SF6. If we have the number of ligands 4, then we have 4 electron pairs around the metal ion. The shape will be tetrahedral. The angle will be 109.5. An example is copper Cl4 minus 2, like methane. If we have 2 ligands around the metal ion, then the electron pairs donated will be 2. The shape will be linear, as I just draw it, the silver, surrounded by 2 ammonia molecules acting as a ligand. And of course, the positive charge on the silver, we draw it outside the bracket, like simple compounds, beryllium dichloride. Okay, of course, we have different octahedral complexes. For example, we can see examples of octahedral complexes, Mn H2O6 plus 2. Mn, which is manganese, surrounded by 6 water molecules acting as ligands, and the manganese ion is plus 2. We show it outside the bracket. Hexa, aqua, manganese, 2, because water is neutral, so manganese carry its charge. Don't mind the colors now. We are going to see many colors, inshallah, next time. Another example is, not always be only one ligand. It could have more than one ligand bonded to the same metal ion. For example, here we have iron, H2O4, OH2. You see iron. We have 4 water molecules acting as a ligand, and we have 2 OH ions. You see here, this is called tetra aqua dihydroxo. We said that OH, we call it hydroxo. So tetra aqua dihydroxo iron 2. You see here, the complex does not have any charge. The complex here had plus 2 charge because all the ligands are neutral. So the manganese still has its positive charge, the plus 2. Now, what happened here? Abrar, why this complex does not have any charge, ya Abrar? Do you know, ya Abrar, why this complex doesn't have any charge? Yes, excellent, ya Jumana. Okay, Jumana, would you please, do you have a mic, ya Jumana, or you don't have a mic?
Yes, I do.
Tab, okay, would you please show us why this complex has no charge?
This because it has 2 ligands, which are the OH minus ions, so they
Yes.
cancel the overall charge of the complex.
Yes, excellent. Because iron, as Jumana said, has a plus 2 charge. And now we have 2 negatively charged ions, which are the OH ions. So 2 negative will cancel with the 2 positive, and the net charge will be 0. It's a neutral complex. We call this a neutral complex. It is tetra aqua dihydroxo, iron 2, which is pale green in color. As I told you, don't mind the colors now. For the last complex, as an example, of course, it's not these only complexes, but these are examples. We have hexahydroxo. You see, the charge here is negatively charged. That's why we say chromate. Whenever the total charge on the complex is negative, we say 8 at the end. So we say hexahydroxo chromate, and then since we have 6 OH ions having -6, and the chromium at the beginning has +3, so the total charge on the complex will be, the chromium SSN has +3, so we write chromate 3 between brackets. But the total charge will be -3. We have 6 OH ions, each having a negative charge. The chromium at the beginning is chromium +3, and we have 6 OH ions. So 3 positive will cancel with 3 negative, and we are left with the 3 negative that is written at the brackets of the complex. So as you see, the complexes could be positively charged, they could be neutral, and they could carry a negative charge as well. Understand? Let's take this ونخلص. Okay, copper, as we said, we have tetrahedral complexes. This is an example. Tetrachloro, tetra, because we have 4 tetrachloro, copper, copperate, because this carries a negative charge. So we say tetrachlorocopperate 2. We say copperate 2, 8 because it has a negative charge. And this is the Tollens reagent that I talked about, which is the silver amine complex. Okay, do you have any question for today? Do you have any question?